in this presentation, we will be talking about a few more aspects related with the fundamentals of welding processes. So, here these are the various aspects about which we will be talking, like unique features associated with the joining of metals by fusion welding. Okay. Then what are the various factors that we should consider while selecting a suitable joining process or welding process. Then mechanisms of joining based on the kind of the filler metal is being used or filler metal is not being used, or solid state joining process is being used under with the limited heat or with the excessive heat. So, what are the various mechanisms responsible for development of the joints? About that we will be talking. Then classification of the joining process, what are the various factors based on which the joining process can be classified, about that we will be talking. And then what is the role played by the heat, pressure and filler metal in joining of the metals, whether it is solid state joining or a fusion welding based process. Okay. So, as far as the unique feature is concerned, like we just try to see here, like these are the two components to be joined. Like say this is the front view and in the top view it looks like this. Okay. So, the line of the weld is this one. So, for development of joint by the fusion welding or by the solid state processes, say for the fusion welding, what we have to do, we have to supply the suitable, using the suitable heat source, we have to supply the heat, so that the melting of the fang surfaces along the joint line takes place. So, the melting will be happening along all this joint line. Okay. And as the loss of heat takes place from the melted portion, that is the weld pool, the solidification of the weld metal will be occurring and producing the metallic continuity. So, this is how it will look like in the front view and the top view. So, we are supplying heat for melting, but the heat application, if we see, this is happening over a very small area. So, that is why what we say, this involves localized heating. Okay. Localized heating means there will be localized thermal expansion, localized contraction due to the cooling that will be happening, because whenever the welding is done, fusion welding is done, initially there will be heating followed by the cooling. So, during the heating the melting will take place, and during the cooling solidification will be occurring, and then shrinkage will be happening. So, as far as the unique features are concerned, the first is the localized heating. Okay. And because of this localized heating, and when like say the heat source is passing along this weld line, so the zones which are being approached by the heat source, they will be experiencing the heating, and once the heat source has passed through a particular region, then they will be experiencing the cooling. Okay. But each zone along the weld line, each zone in vicinity of the weld zone, each zone in vicinity of the weld line will be experiencing the different heating and different cooling conditions. Means the rate of heating, peak temperature and the rate of cooling, that will be experienced in the different locations in the zones close to the weld line, that will be different. So, this is with regard to the kind of thermal cycle that will be experienced by the different zones, especially in the fusion welding. So, localized heating, that in turn will be leading to the differential heating and cooling conditions. So, if you want to understand this, we have to simply see the thermal cycle experienced. Say if we have a weld zone like this is the weld area. So, location 1 and location 2. So, for the location 2, say for the thermal cycle for location 1 is like this, and thermal cycle for location 2 goes in like this. Okay. Just a minute. So, thermal cycle for the location 2 will be happening like this. So, here lower peak temperature at the location 2, lower heating rate and lower cooling rate. So, here in x axis we have time and y axis we have temperature. So, this variation in temperature as a function of time of a particular location is known as weld thermal cycle. So, weld thermal cycle for each location is different, and that is why what we say differential heating and cooling conditions are experienced by the metal during the welding. Okay. So, because of this localized heating and a differential heating and cooling that is experienced in the different zones in vicinity of the weld joint. Because of this, what we see that there is a development of the residual stresses, because the differential expansion and contraction experienced by the different zones in vicinity of the weld joint, that will be leading to the development of residual stresses. Most of the time these residual stresses are tensile in nature. So, when tensile residual stresses develop, our tensile load carrying capacity is very badly compromised. Okay. Another thing that is experienced is the partial melting, like say when this is the one component, it is being, so when surfaces are brought to the molten, so this zone has been melted. Okay. But next to that area there will be a mushy zone, especially in case of the alloys, where we will have both liquid and solid. So, it causes the partial melting in especially in the alloys having the wider solidification temperature range, and this in turn promotes the liquefaction cracking. Okay. Then the unique weld thermal cycle, as I have said, each location next to the weld joint experiences a different thermal cycle. So, the point very close to the weld zone, that will be experiencing the higher heating rate, higher cooling rate, higher peak temperature, and as we move away from like 1, 2, 3. So, 1, 2, 3, and this is temperature and this is time. So, heating rate, cooling rate and peak temperature, all three get reduced with the increase of distance from the weld zone in case of the fusion welding. So, unique weld thermal cycle is experienced by each location in vicinity of the weld joint. Again, it will depend upon the multiple factors like the kind of heat that we are supplying and thermal conductivity, the section thickness. So, these are the factors that will be affecting the kind of thermal cycle that will be experienced by a particular location. Okay. Then we have the chemical, mechanical and metallurgical heterogeneity. During the fusion welding, whenever we heat, so the one zone will be brought to the molten condition. So, on solidification, this will be resulting in the cast structure. Okay. Then the zone next to the fusion zone will be experiencing again very high temperature, and this high temperature will be leading to the development of the zone which is affected by heat delivered. Okay. And then there will be a region which will not be much affected, that will be termed as base metal or the parent metal. So, three zones are commonly formed, like the weld zone, heat affected zone and the base metal. Each zone differs in terms of the microstructure and mechanical properties, and that is why what we say, we have the chemical, metallurgical and the mechanical, metallurgical and chemical heterogeneity. Chemical heterogeneity especially is observed when we use the filler metal of the different composition. Okay. So, if the say this is the mild steel, base metal is mild steel, and for the sake of the like say reducing the residual stresses or for better corrosion resistance, we may use stainless steel or we may use nickel alloys. In that case, the weld metal will be of one composition, heat affected zone will have that heat affected base metal will largely have the same composition. So, the weld joints can experience the chemical heterogeneity. Certainly, the mechanical heterogeneity exists because of the microstructural changes. Okay. Now, whenever we take any metal, like say this is a metal, it will be offering certain yield strength, certain percentage elongation, certain toughness, okay, and certain fatigue strength. Okay. So, but when we develop a weld joint of the same metal, what happens because of the development of the residual stresses, microstructural or metallurgical heterogeneities and development of the cast structure and development of the notches in form of like the weld toe or the defects like cracks and porosity. So, these factors in turn lead to the reduction in the mechanical corrosion performance of the weld joint. Say your base metal will be showing one set of the mechanical properties, corrosion resistance, but when we produce a weld joint of the same metal, the performance of the weld joint with regard to the mechanical and corrosion performance is very badly compromised, and therefore, and that happens particularly due to the localized heating or a localized deformation that is used in case of the solid state joining. So, the reliability of the fusion weld joints especially is compromised very badly as compared to that of the corresponding parent metal. Okay. And a few metals like the mild steel and alloy steels, okay, alloy steels, when a weld joint is developed of those the steels, what we find like the ductile to brittle transition temperature means the temperature at which sudden loss in toughness of the weld joint that will be occurring is badly compromised. So, we always want that this transition occurs at lower temperatures. So, if this transition is happening say minus 40 degrees centigrade, then we hardly be coming across such kind of the low temperatures. But if the transition is happening say at 0 degree centigrade or 10 degree centigrade, then it will be a great problem, especially why, because the weld joint can frequently come across such conditions of 0 degree or 10 degree centigrade, and under those conditions if there is a loss in toughness, then our performance of the joint will be badly compromised because of the reduced toughness. So, in y axis here we have toughness and x axis we have temperature. So, here increasing temperature. So, I will redraw this. So, it goes in like this. So, in y axis there is a toughness, okay, and here we have temperature. So, say this temperature say plus 40, 30, 20, 10, 0, minus 10, minus 20 like this. So, we may come across the variation of this kind. This is one variation, okay, where the drop is experienced like say between minus 10 to 0 or so. But there is another possibility that this drop can take place at much lower temperatures. Okay, this drop can take place as this continues to hold the toughness even at a lower temperature, and then drop is occurring minus 30, minus 40 degrees centigrade. So, this may be true for the same simple base metal, okay, but when the weld joint is developed, this drop starts occurring at a higher temperature, and that is why what we say that the weld joints of certain metals increase the ductile to brittle transition temperature. Say which say a temperature for a metal is minus 20, but if it is reduced to minus 10 or 0 degree centigrade, means if it is increased from minus 20 to minus 10 or 0 degree centigrade, then this will be compromising the performance of weld joint very badly, because the joint can fail in brittle manner because of the reduced toughness. Similarly, because of the significant refinement of the grain structure in the heat affected zone, the creep resistance of the joint is badly compromised. Okay. Then softening and hardening can also occur, like certain steels, Q&T steels means quenched and tempered steels. If we try to study the hardness profile across the weld joint, then we may come across situation here the weld hardness may be high like this, but the hardness is compromised. So, this drop in hardness of the HZ is attributed to the over tampering in case of the Q&T steels, but simple hardening or hardening will be taking place in the weld zone primarily due to the austenite to morticitic transformation even in the Q&T steels. So, HZ softening occurs in Q&T steels, otherwise the metals in normal annealed condition or in normalized condition, they will be showing hardening of the heat affected zone. So, hardening of the heat affected zone can be observed like this. So, this is the HZ, okay, and this is the weld zone. So, if you want to see the hardness, so the hardness of the weld zone can be changed as per our convenience by using the suitable filler metal. So, this is the hardness of the HZ. Say if you use the filler metal, then the hardness of the weld nugget or weld zone will be lesser than the heat affected zone. So, the heat affected zone can experience the higher hardness or the lower hardness depending upon the metal or depending upon the condition in which the metal is. So, as Q&T steels they experience the softening, but the steel in the annealed condition they will be experiencing the hardening. Okay. Then, so since there is a lot of heterogeneity in terms of the composition, microstructure and mechanical properties, and which in turn adversely affect the mechanical performance as well as the corrosion performance. So, To improve the properties of the weld joint, sometimes the weld joint for critical applications need post weld heat treatment. So, this is done primarily for improving the microstructure, improving the mechanical properties, and also reducing the residual stresses if these have developed during the joining process. So, these are the various factors which make the fusion welding very unique as compared to the other manufacturing processes like casting, forming or machining. Okay, so next is the selection of the joining process. If we see, so we can talk about like solid state joining is one, the fusion joining is another, and solid liquid joining like the brazing and soldering is the another one. So for solid state joining, it is important that material is preferably having the lower strength and higher percentage elongation, especially those solid state joining process which are based on the plastic deformation at micro level. For fusion welding, it is important or it is preferred that like the melting point is a little lower, thermal expansion coefficient is also lesser, solidification temperature range is lesser, so that the issues related with the welding are less. In case of the solid liquid metal joining like the brazing or the soldering, we do not need the melting of the base metal, we need just melting of the filler metal, but this will be preferred only when the little lower strength base metals, lower strength joints will also be fine for the given performance. So, what we need to see, not very heavy section joints or heavy section components are welded using the solid state joining, but the fusion joining certainly can be used. So, the factors that we need to consider is like thickness. So, for low or moderate thickness maybe we can use solid state joints, but for a very wide range of the thickness like say 0.5 mm to even 300, we can go for the fusion joining without much difficulty. Okay. So, although we have to choose the suitable process in such a way that we can deal the wide range of the section thicknesses which are to be used for joining. Okay. Then the melting point, it is preferred that metal is having the lower melting point, so that it can be brought to the molten condition by the fusion welding process. If the melting point is high, then again it will be of greater hardness, greater strength, which will make the solid state joining also difficult. Then thermal expansion coefficient, higher the thermal expansion coefficient. So, if the thermal expansion coefficient is high, then we need to see that not much heat is supplied during the welding, so that heat joint is developed using the lesser heat input, so that the issues related to the differential expansion and contraction in the different zones, those are minimized. Okay. So, maybe when we go with the laser welding or electron beam welding or even TIG welding, the issues related with the differential thermal expansion coefficient, that will be less in the different zones, and that is the concept which is used when we are dealing with the dissimilar metal combination. Like say, if we have to join the same metals, then certainly we can use solid state joining or the fusion joining as per the economics and the performance requirement. But there, if we are dealing with the different metals which are not compatible with each other in terms of the mechanical, chemical and the physical properties, then we need to see like A and B are handled with the greater care. So, what we prefer is the solid state joining, so that the interaction between the two is minimized and they are not brought in the molten condition. And if you have to use the fusion joining, then we need to be very careful, because if A and B are not compatible with each other, then they should not interact with each other much, and therefore, we may use the filler metals such that they are compatible with both A and B. So, filler metal C is compatible with A, B and A both, then the fusion welding in this scenario will work in better way. Or we use the transition joints like A and B are isolated or they are connected through the A and B, and we use the C is the third metallic element as a small part. Okay. So, these are called transition joints or tri-metallic joints. Okay. So, in that case we need the two different the joints for making. So, the A and B will be connected through the C small member between the A and B, and then the two additional weld joints will be developed. So, depending upon the metal combinations to be used for development of the joints, we choose the suitable welding process. Okay. And then we have the criticality of application. If it is like the, if we are dealing with the non-critical applications, okay, where even if the failure of the, where the loading conditions are not very severe, or the service requirement is not very critical from the life and the property loss point of view, then we may go with the fusion welding processes which are economical and efficient. Say, so shielded metal arc welding and like say the gas welding. So, these are for use for general purposes. Okay. But if we need a little better industrial quality weld joints for the good performance, then we can go for the gas metal arc welding or submerged arc welding process. If you want to go with the further higher, if the expectation from the weld joint for the performance is very important for the functioning of the system, and so we need to have very reliable joints for the critical applications, then we go for the TIG welding or for the laser welding or electron beam welding. So, here say for nuclear applications, for pressure vessels, and for all critical applications, aircraft component fabrications as per the need. So, these welding processes are used. So, the criticality of the application significantly affect the choice of the process to be used. Like say there can be another scenario where we go for the systems for critical applications, where not just the loss of life is important, but also the long term performance is also important. So, there what we do, we go for the application of the hybrid joining. So, in hybrid joining what we will be doing, we will be using the two processes together for improved joint performance. So, it is usually very common, like adhesive joining is clubbed with the fusion welding, spot welding, or solid state joining. So, when this kind of clubbing is done, this helps to improve the performance of the joint. But when the fusion welding process are clubbed like the TIG with the MIG or the laser with the MIG, then these will be increasing the speed of welding and the productivity. So, the economics of the welding process is improved. Okay. Then the property and performance requirements. So, if we do not want much compromise in the properties of the parent metal due to the welding, and we want very high performance, then we will go for the low heat input process. Okay, low heat input process. So, our TIG welding, laser welding, electron beam welding, plasma arc welding, electron beam welding. So, these will be preferred, but if the compromise in the property is not that a major problem, or if the performance is not that critical, then we will be going for other welding processes like shielded metal arc welding, sub arc welding, MIG welding, like this, and the flux core arc welding. So, there are numerous welding processes. Eventually, if whatever is being made, that should serve the purpose with the great reliability. So, at the end, if we are able to make the joint in such a way that it delivers the desired performance for designed life, then we need to see that which approach is to be used for development of the joint, so that the joint can be made economically. So, economy is the one and very important aspect in selection of the joints, because at the end of the day we have to see that which approach can be used for development of the joints economically. As far as the basic mechanisms are concerned, like say in case of the fusion welding, when the edges of the components are brought to the molten condition, then if we do not use any filler, just the edges are brought to the molten state, then we allowed to solidify. Then partially melted grains act as nucleants, and the growth of those new grains directly starts by consuming the molten metal. So, in case of in such situation where we do not use any filler, or filler of the exact same metal as that of the parent metal is used, then there is no nucleation stage in solidification, direct growth takes place. Okay. So, this kind of the solidification approach is known as epitaxial solidification, which directly involves growth, no nucleation. But when we deal with the different filler metals, like say the two components of the same metal, when they are being welded, by the different filler metal, say B, due to the, like say, for reducing the residual stresses a particular metal is being used, or for achieving the particular combination of the properties, like say stainless steel or the filler metal, nickel filler is being used for the mild steel or for cast iron welding. In that case, what will be happening, the different filler is, if the different filler is being used, then the solidification of the weld metal will certainly involve nucleation and then growth. So, this is the conventional heterogeneous solidification that will be happening. Okay. So, this is about the melting and solidification wise how we can the group the fusion welding based processes. Then the deformation based processes like solid state joining involving recrystallization or no recrystallization. So, there are few processes which are carried out under at room temperature or just above the room temperature, which is not high enough to cause the recrystallization of the metal. So, if that is the case, the joint is being developed using the cold deformation based approach, where temperature rise is not much. Then this will be involving great plastic deformation at the interface for mechanical interlocking, and when this will be happening, the material will be strained heavily. The lattice will be strained heavily, and this will be causing the work hardening and the strain hardening kind of the effects apart from the grain refinement. So, we may find in this situation, like due to the work hardening, the hardness at the interface is higher as compared to that of the parent metal. This is a scenario when there is no recrystallization, only the lattice is getting strained and leading to the work hardening effect. So, this may happen like in the cold welding conditions, especially when not much of the heat is generated. So, whether it is the ultrasonic welding or the deformation based approach of the forge welding, then under those conditions the joint or cold welding simple, the lattice will be strained coupled with the plastic deformation, and that will be increasing the hardness and the strength at the joint interface. When the plastic deformation, whether it is micro level or macro level or micro level, the deformation is used for development of the solid state joint, then this, and if the temperature is greater than the recrystallization temperature under the hot deformation conditions, then this will be leading to the recrystallization. Okay. And the recrystallization means the effect of work hardening will be minimized, okay, and the newer grains will be formed, will not have any the elongated grains, but whatever the effect that will be experienced by the grains, that will be neutralized due to the dynamic recrystallization that will be happening during the welding at a higher temperature above the crystallization temperature. So, the solid state joining, like whether it is like the friction welding or the friction stir welding or the hot forge welding. So, under those conditions, what we will see, there will be deformation, but deformation coupled with the recrystallization, that will be leading to the reduced work hardening effect. Then in case of the liquid and solid state joining, like as I said, we use the filler metal, like component A and B are being joined, components are heated, then we put the filler metal in form of the brazing or soldering material, which on melting gets spread at the interface by the capillary action, and on solidification we get the joint. Okay. Diffusion based processes where atomic diffusion across the interface is responsible. So, diffusion based process like diffusion bonding, this process is slow, like these are two components. So, these are like very smoothened, flattened, and then kept at a high temperature under pressure in a vacuum chamber like this. So, vacuum chamber, high temperature and under pressure. Okay. So, these are the three: vacuum, temperature and pressure. So, when the two components are brought in perfect metal to metal contact conditions at a high temperature, diffusion across the interface takes place, and that in turn leads to the development of the joint, but it also leads to the recrystallization and forming the new grains at the interface. Since the process is slow, it is entirely based on the diffusion. So, certain diffusion accelerating approaches are used, like use of the ultrasonic vibrations during the joining, so that it can improve the metallic intimacy. Same is the role of the pressure pulsation and the interlayers. So, interlayers also helps in improving the metallic intimacy. At the same time, this also acts as a diffusion accelerator. Okay. Now, we will see the classification of the welding processes. Here classification. So, we can classify the welding processes or joining processes based on the multiple factors, whether there is use of heat or no heat, whether the use of pressure or no pressure, or there is a filler or no filler. So, in solid state joining, we assume that the heat will not be supplied much from the outside, or heat is supplied, even if the heat is supplied, then it is not supplied so much that there is any melting. So, we have to avoid the melting, but heat is supplied primarily for softening the metal and improving the diffusion. Okay. In fusion welding, heat is supplied for realizing the molten condition, and then we can have the high and low heat input welding processes like ultrasonic welding, which generates very less heat by the interfacial friction, and the more heat like the friction ester welding or friction welding, they generate lot of heat during the welding. And then autogeneous or the heterogeneous welding process, like autogeneous one, where the edges of the components are brought to the molten state without using any filler metal, and followed by the solidification, that will be leading to the autogeneous welding. In heterogeneous welding, what we do to deal with the, either we have to fill the gap. If the edges has been prepared, then gap has to be filled, so we use the filler metal. Or if we have to, or if we want that A and B being joined are not compatible with each other, so C is to be brought in, so that it improves the compatibility between the two different metals like A and B. So, or we want certain specific set of the properties that is needed for development of the joint. So, heterogeneous welding means we use the filler, which is not exactly same as that of the parent metal, for the requirement of the specific properties, okay, for improving the compatibility or for filling the gaps, okay, if the groove has been prepared. So, in these conditions we will have the heterogeneous welding if the filler metal of different type is being used as compared to that of the base metal. And when the processes are classified, so what is the purpose of classifying the processes? Like grouping based on the similarity or the dissimilarity. When we classify, then we need to see really on what basis the processes are similar or they are different. It also helps in giving the newer name to the new processes which are being developed. So, nomenclature for the newer processes for easier communication, like solid state joining, where there is no melting. If there is a melting, we will say that the fusion welding based processes, and it also helps in proper organization of the facilities and the things, so that the people have the suitable expertise. Okay. This is just the overview of the set of the welding processes. So, we have cast welding process, fusion welding process, resistance welding process, solid state welding process, and metal deposition. These are the allied processes. So, in cast welding we have thermite welding and electrostatic welding. In fusion welding we have carbon arc, then sealed metal arc, submerged arc, gas metal arc, and all these the processes where the fusion of the fin surface, melting of the fin surfaces is needed. Resistance welding process, where the heat is generated by the electrical resistance principle, joule heating basically. And in the solid state welding process also we have low heat, like the ultrasonic welding, cold pressure welding, and explosion welding, and high heat in process like friction welding, force welding, and diffusion bonding. Okay. Cast welding process are those where the metal is fed from the outside, molten metal is fed from the outside, okay, or the conditions are similar to that. Okay. The conditions are similar to that means the rate of the cooling which is experienced by the molten metal during the solidification is very low. Okay. So, in case of thermite welding, what we do, we supply the molten metal from outside at the interface, and once the molten metal is filled in by the heat dissipation from the molten metal, solidification takes place and the joint is developed. In electroslag welding, the conditions are, you see, the heat is generated at the interface and the things are brought to the molten state coupled with the melting of the parent metals and the filler metal both, but the cooling conditions are similar to that of the, means the cooling rate experienced by the weld metal during the solidification during in case of the electroslag welding is similar to that of the casting process. Okay. So, now I will summarize this presentation. Basically, in this presentation I have talked about the what are the various factors based on the which the process can be classified, and what are the mechanisms associated with the development of the joints, and what is the unique features, what are the unique features associated with the fusion welding process. Thank you for your attention.